2013 higher level DCG B1. The image below shows Fountain Place, a skyscraper in Dallas, Texas. The building was designed as a large glass-faced building which the architect described as what's left after carving into a square prism. Figure B1 shows the plan and elevation, excluding hidden detail of the structure. Part A is draw the given plan and elevation of the structure. Part B, determine the dihedral angle between planes A and B. Part C is determine the true shape of the vertical surface A. And final part is the director of a future Mission Impossible movie wants to shoot a scene that involves climbing the outside of the building. A stuntman is to travel down from point S along surfaces A, B and C to the ground. Determine the projections of the line on each plane that the stuntman must move along so that he travels the shortest possible distance on each successive surface as shown on the right. Scale for this question is 1:2000. So setting up this question, I'm going to start by drawing the plan first. So I can keep that down low. And it's 50 millimeters or 50 meters by 50 meters when scaled down is 25 millimeters by 25 millimeters, so it's 50 millimeters square. And then we'll just find the rest of this, so having it. Okay, so darkening in the plan. So projecting our elevation, we don't need to worry about the hidden detail. So again, we're marking in our heights, so 50 meters becomes 25 millimeters. 100 meters is 50 millimeters. And then another 25. So that completes the elevation of the plan. Just watch out for projecting all your points up that you're taking to the correct line up above. So that's part A done. Part B is to determine the dihedral angle between planes A and B. So this is plane A, this is plane B. The common line between them, or the line of intersection, is this one here. So in plan, that would be this line down here. So this is looking on B, C is in here, and A is in there. So that's this line here. So to find the dihedral angle, we're going to find we first need to find the true length of that line, and when we have the true length of the line, then we can get a point view of it. And when we have a point view of something, we are able to get when we have a point view of something, we see an edge view of the two planes. So I'm just going to position this here. So this is my x1, y1 line. And projecting these points up, so we're going to take our heights from, so working this view, skipping this view, taking them from the elevation here. So this point on the line of intersection, measuring up our height on the same line up here, marking that. That's that point. The other end of that line, the line of intersection, measuring up the height, marking that up here. This line here is now the line of intersection. Finding the other points, so finding the plane B, the last point on that. So following up that point, that's here. And then finally plane A. Now, if you look at the state exam solution, you'll see that they don't take an additional point up here, because they're just taking a lamina. So what they're doing is they're taking that whole plane and just part of this plane. So from this point to S to here, it still gives you the same result. You're just leaving out that top point up there. So it's not important. You don't need to do it. So measuring up the height of point S, locating that up in our auxiliary elevation. So you can join this point back up to here if you like. I'm going to put in the apex. So this is now surface A. So joining all those points together. Now, as I said, you don't need to put in this point. You could just put in going from here across. That would give it'll still give you the same result. Okay, now that we have the true length of the line of intersection, we're going to look in perpendicular to that. We're going to take a point view of that line. So we're going to project all our points down along here now and put in another XY line. So this will be your X2, Y2 line. Tidy that one up a bit. So projecting each point down into the view. Now our distances for this view are taken not from this one, working from our plan. So by right we would be measuring from our x1, y1 line back to the plan down here, but that distance is huge. It's too big and it'll bring this off our page, so it won't really work. So what we're going to do instead is I'm going to input in a measuring line. So a measuring line is, I'm basically just moving the x1, y1 line closer to the plan just for the purposes of measuring. So anywhere along here, it's going to be parallel to the x1, y1 line. So anyone here. So this is parallel to this one, which was parallel to the line of intersection. And that's just my measuring line. So I'm going to just use that to measure distances for my second auxiliary instead of having to take them from back here, so I'm cutting out this much space, this much distance, which is there on my page, so it would stop it from going off the page. So taking each point, so this point here, this line of intersection, measure the distance from my measuring line back, so that will be the same for both points as it's parallel to it, and it's a point view here, so that gives me this point here. So this is a point view of the line of intersection. Next, what we're going to do is going to take the distance from to this point, so I'll be able to draw the edge view of surface B. So that's this point, follow it into this view and out. So that's the other point on surface B. So this line here now is an edge view of surface B. And to get the other 2 points, measuring the distance, so from the apex, the top of the roof, that point to here, which is this one, and it's the same distance to the other point here, so I can mark that one also. And this is the edge view of surface A. So edge view of surface B, edge view of surface A, and in here is the dihedral angle. We're not asked to measure it, so you just need to determine it. This is determining the true shape, or the dihedral angle between planes A and B. So looking at the question again, the next part of this is to determine the true shape of the vertical surface A. So this is our vertical surface A. We need to determine the true shape of that. Now the true shape of surface A is technically done over here. We've looked in perpendicular to it, taken an auxiliary and found the true shape. What they want us to do is they want us to do it up here as a rotation, because it's going to help us with the next part of the question, which is to determine the shortest line from S onto surface B and down to the ground. So it's an unusual question that they kind of want you to do it here again. So this is technically the true shape, but I'm going to do the rotation method over here just so we can get the next part of this, which will help us with part D. So what we're going to do is we're going to rotate surface A from this position around till it's horizontal, so that in the elevation we're going to be looking in perpendicular to it and get the true shape of it. So to do that, I'm going to take a horizontal line from, I'm going to use the line that S is on as my hinge, so I'm going to rotate around that. So point my compass on where S is, extend and rotate that to this position, do the same thing for the apex, the top of the roof, the point of the roof. Swing that around also. So finding, this gives me the new width for surface A in the elevation. So if we're to take this point here first, that now comes over to this point, so it's not going to move up or down. All we're doing is turning it sideways just like a door, so the handle stays the same height off the ground. So that's going to come to this point. The ridge, this point here, we rotate it around until it's horizontal. That gives the new width of it as this point here. So just showing what that looks like. The true shape goes from point S to this one up here, to the new position for out this corner, back to this point in the corner with where line S is. So that pink area here is the true shape of surface A. Of this question, the mission possible part of it, stuntman is to travel down from point S along surfaces A, B and C to the ground. Determine the projections of the line on each plane that the stuntman must move along so that he travels the shortest possible distance on each successive surface as shown on the right. So just going to have a quick look at something on this first. So if we take surface C first, the shortest distance here is going to be, if we're going to go from this point here to this point down here, that's going to be a sloping line on the surface. That's not going to be the shortest line going from that point to the ground. The shortest point would be a vertical line coming down along it here, so perpendicular to the base of it. Same principle is going to kind of apply here. So the shortest distance, we're going to avoid the diagonal lines. So if I'm going from here to up here somewhere, that's a sloping line and that's going to be longer than a horizontal line on the surface here. So then for surface A, we need to just figure out where we're starting, because once we have the point between surface A and B, it's going to be a horizontal line and a vertical line, so that part will be straightforward. Part S, starting at S is where we need to first figure out where we're going, and the shortest distance between something would be a line perpendicular to it. So if I have a point going from here back to S, that'll be longer. So if I was to basically have circles, it would go beyond it. So we want to find the shortest point from the line of intersection between A and B to surface S. To do that, we need to have our true shape. So if we don't have the true, if we just use this true shape, we need to draw the true shape here, because the only way we can find the perpendicular, the shortest distance between the pink line and surface S, or the line of intersection, is that if we have a true shape of it. So in the elevation, we're not looking at the surface A correctly, we're not looking perpendicular to it. So what we might draw as perpendicular isn't actually a perpendicular line to surface S. So we're going to draw a perpendicular line, but this time from the pink line. So it's a line perpendicular to the pink line to surface S. And that gives me the shortest line on the surface, on the pinks, so on the true shape of the surface. So this here would be perpendicular, so that gives us the shortest distance. So if I was going from this point to a point over here, that would be longer. So that gives us the shortest distance on the true shape. So now we need to find it on the elevation. So that was it rotated out into this position. So if it's rotated back, it's going to be horizontal from where it is. So if I bring a horizontal line back to here, that point here gives me the true position for the shortest line. So from that point now, surface S to that point, that is one line. So that is the shortest one. So what I've done is I've taken a line perpendicular to the true shape, the pink line, from point S, and then I've had to bring that horizontal back to the actual, to our rotating it back into the position in our elevation. So when I drew it on the pink line, I drew it out here in the rotated view, but I have to rotate it back into its correct position in the elevation. So that gives me that point there. So that's finding it on surface A. So we're going to locate this point now down in plan. And that gives me this point here. So this is, so our line on the surface from A goes from here to here. To find the next piece, we need to do it in plan next. So again, we're going to find the shortest distance, and again that's going to be perpendicular to this here. So it's going to be a perpendicular line. So it's perpendicular to the edge of surface B. That gives me this line. So we can locate that up in the elevation now. Give me that point. Now it appears as horizontal. So, but it's perpendicular in plan. So that's the shortest distance. If we were going that way or that way, it would give me a longer line. So finally then, getting the last bit of this, that's the surf transition between B and C. Same point up here, vertical line down there. And that completes the 2013 higher level B1.